court. All right. So last day, just as review, right, we talked about Anova, which is comparing numerical data across categories, right? So across multiple groups. Comparing numerical, oh, I guess I should say what I'm talking about. Anova. Which was comparing. And then, oh, now it's all coming back to me. Then we tried to go see the puppies. The puppies were gone. You guys already seen them. I missed out. Oh. Come on. And we were here talking about Anovas. Comparing numerical data across groups, right? More than two groups. More than two groups. Right. If you just have two groups, you could use a two sample t-test instead. That's probably more efficient. So more than two groups, which means that they have, this is a categorical. Variables.
So the formulas are similar, right? Which you already did in Statistic.
Yeah. So the formulas are the same, but then what we did was we introduced this resampling, which we're going to look at in the lab, right? Where we resample and then we're going to compare. Okay, well, if I do this kind of bootstrapping, right, where I'm resampling and I'm just generating a bunch of different scenarios and then finding the probabilities, how does that compare to kind of those formula ways that we were using in Stat 230, right? And so so here, right, let me make sure that this makes sense because so far it hasn't. Anova is comparing numerical variables or one numerical variable at a time, right, across more than two groups, which would be across a categorical variable, right? So then the other option, if I have two categorical variables, I can have some categorical outcome, right? And then I could look at it on its own, right? Or I could do a 2x2 table, or sorry, a two-way table for two categorical variables. So today, we are gonna just look at the chi-squared test, right? I know we've already done the chi-squared test, and so for that reason, I want to kind of walk through the resampling. But at this point, right, we've talked a lot about the different resampling, and so the idea stays the same, right? We're going to do this permutation test where we throw everything in, and then we generate, okay, just randomly regenerate the data, and then we use that to figure out how rare our observation was, right? It does require kind of some knowledge about the theory. Locked from the inside. Right, so we'll kind of review some theory, but then the idea stays the same, right? So we'll do a compare and contrast where we're going to use the permutation test, and then we're going to use the kind of the theoretical chi-squared test, and we'll compare them. Okay, so today we will talk about the chi-squared test, right, which compares, or it considers one or more category, or I guess I should say just one or two, which considers one or two categorical variables. Yeah. So usually we'll leave Anova in the dust. And I guess before I get too far, maybe I'll have it up here so that when someone opens these notes later, right? Reminder that test number 1 is on Tuesday, right? Next week. Yes. Tuesday.
And what chapter?
1, 2, and 3. And I'll keep it easy. I'll keep it with the assignment questions, right? Just so we have an easy test and then see what I do for test 2. All right. Easy.
So it's on Moodle or on paper?
On Moodle. Yeah. So you'll bring your laptop in. We'll sit here. I'll watch you do it. You submit your answers. Any written work, you'll just hand it in to me, just kind of as a backup. And then that'll be good. That's how I want to do it. Okay. Good. Had to get that off my radar. Test 1. So the chi-squared test. Let's do a little bit of a kind of jog through chi-squared tests in general, right? So for us in data science, what we're going to use the chi-squared test for most of the time is just testing independence, right? Are these two things independent of each other? Or did I see a difference between these two groups, not just by chance alone, right? And so that's something that we're going to be interested in. Not so much are they significantly different, right? Unless, we're talking about kind of generating money, right? But we want to see, okay, is this website better, right? Do people click on my ad more here or here or here? Or is it just random chance happening all over the place, right? That could be the case, right? So a chi-squared test chi-squared test compare counts across groups. Okay. And we're usually going to use it for more than 2 groups, because if we only have 2 groups, we could use a z-test, right, for proportions across the 2 groups, right? And so P1 hat, P2 hat, that kind of thing, which we've done, right? So now usually we use it, you can use it for 1, or for 2, but no. So chi-squared test compare counts across groups and usually more than 2 groups. So in data science, we're going to use chi-squared tests to test for independence. Now the chi-squared, just like an F-test or just like a t-test or a z-test, can be applied to different scenarios, but for us, we're just going to focus on independence. Okay. So in data science, I made that look like one word. We focus on tests of independence. Tests of independence. So that is things like, is this website generating more clicks, right? Significantly more clicks than this other website or these other websites, right? Or is this just happening by chance alone? Maybe I'll put it on a fresh line here. So that is does this website generate more clicks than other websites? Or are the differences that we're seeing, are they by chance alone or due to chance alone? Or are the differences we're seeing due to random chance? Right, so that would be the test of independence. Yeah. So that means that we're going to have some expected distribution, right? And that's kind of at the heart of the chi-squared, is we compare our observed counts to the expected counts. So chi-squared tests compare observed counts to expected counts. Oops. Oh. Okay. Now I think I'm gonna so like I said, chi-square tests, we can look at one categorical variable, or we can look at two categorical variables, how they compare to each other. But the idea stays the same, right? You're gonna have your observed counts and your expected counts, and then you're gonna look at the difference. You're gonna square those, you're gonna take the, right, kind of, there's some other stuff in there, and then you add them all up, and then that's your chi-squared test statistic. But in general, it's just the difference between your observed and your expected, right? And so we can consider one categorical variable, right, which might look something like this. A, B, C, D, right? Just generic groupings for one categorical variable. Right, let's say those are grades. And because I have some numbers here, right, if I do your observed counts versus your expected counts, I had 14, 21, 19, and 15, which puts me at a total. Oh, I should put that down here, of 69. If I'm expecting the distribution of grades to be just the same across the board, right? So there's the same number in A who get an A, who get a B, who get a C, who get a D, or relatively the same, right? We're expecting some fluctuation, but around the same expected value. Then, right, just looking at this, it looks like this 21 and maybe 19 could be higher than 14 and 15. So that's what we want to find out. So what would we do? We would say, okay, if they're independent of each other, right? So there's no rhyme or reason between what grade people are getting, right? Then I would just take this 69 and divide it by 4, right? And then that would be my expected count in each cell, right? So 69 divided by 4 is an expected count of 17.25. For our expected counts, we're allowed to have decimals, right? We're going to have decimals, that's totally fine. So then I'm expecting 17.25 in each of these cells. putting me at a total of 69 again, of course. Okay. So if there's no, if this is just a random chance how these were distributed, right, I'm expecting things to be around 17.25. Now in this case, right, just by eyeing it, it's kind of hard to say. So we would need to do the calculation, right? And so the calculation is going to be, and I guess it's been a while. Yes. We would calculate the difference between the observed and the expected counts so then we would have your observed minus your expected. This is a new page, so I'll put it up one more line. And then we're going to take divided by the expected, the square root of the expected value. So for each of these, right, I've got 14 as the observed minus the expected, so minus 17.25, and then divided by the square root of the 17.25. But then I have to do that for each of these cells, and then I have to add them all up. So usually we're going to denote this by a capital R, or at least this textbook does. Make a mess here. There. So then chi squared is going to be the sum. If this is I equals 1 to R, right? I should use C because I put it in the columns. That way it'll make sense. C categories. Right. So for each of the categories, I'm going to add these up. So from I equals 1 to C, which in this case is 4, right? Then we're going to do R squared. Right. I'm going to have C minus 1 degrees of freedom if I'm chi-squared distribution, but now we're going to introduce the permutation test approach, right, where we don't need to rely on degrees of freedom, right? And so that's nice, but it's the number of columns minus 1. Or if we have a 2x2 table, right? So 2 categorical variables, I can still find the expected counts, right? And I can still subtract the observed minus the expected, but now I need to take into account that I have across the rows and the columns. So or we can consider 2 categorical variables. Right. So maybe I split these up by gender, male, female, and then the grades A, B, C, D, for example. Then I'm going to let C be the number of columns and R be the number of rows. Right, making this an R by C table. I think the degrees of freedom are R minus 1 times C minus 1, I think, something like that. Doesn't matter for us because we're going to move away from that. But right, so in this case, right now I have to add up across the rows and the columns. So then the chi-squared test statistic is going to be the sum from I equals 1 to C, and J equals, should make that look like a proper J. J equals 1 to R of R squared. Right here, this is the sum over the rows and the columns. Over the rows and columns. But at its heart, right, we're basing it off of R, which is going to be the observed minus the expected over the square root of the expected. And then we have to square it. So you could do that here. There's lots of different ways that you could do it, but the idea is the same, right? It's the difference between the observed and the expected values. Okay. One of the conditions that we have for using, especially in kind of the traditional framework, is that we have to have at least 5 counts in all the cells, so 5 observed counts, because otherwise, if you're trying to determine if things happen by chance alone, but you only saw 2, right, that's going to be hard to kind of recreate, right? And so that will be rare, but maybe it's not that rare. So so just as a general rule, we have to have 5 counts in each of the cells, right? Which sounds easy and attainable, but it's not necessarily, right? If it's something that's really hard to kind of get to, then it's hard to get to 5. Okay? So one of the conditions for using, or a condition, I should say, condition, we need to have at least 5 observed successes or observed, sorry, I just taught the binomial in Stat 230. That slipped out. Still kind of counts, but it's different. Observed successes. I'm sure you guys were like, no, I don't want to. We need to have at least 5 observed counts in each cell in order to use the chi-square distribution. In order to apply the chi-square distribution. If we have less than 5 counts, there's still a way to do that. But what we do is we use Fisher's exact test, which is exactly that, right? It goes through and it generates all the different permutations. So instead of randomly generating permutations, it says, okay, I'm going to look at all the possible ways that I could have this few outcomes, right? And then that's how we find the probability. So it does the same thing, but it generates all the possible outcomes instead of just a random sample of outcomes. So if we have less than 5 observed counts, less than 5 observed counts in one or more cells, we use Fisher's exact test. Fisher's exact test considers all the possible permutations, right? And then tells you what the probability of seeing what you saw is. So Fisher's exact test considers all possible permutations to determine exactly how extreme to right, or the observed distribution of counts is. The observed results, right, or observed distribution of counts is. Yeah. So if I go to the textbook, save us some writing here. They're talking about kind of whether people click on a website, I guess, with different headlines, right? So we've got headline A, headline B, or headline C. And then we're recording whether people clicked or didn't click. Most people don't click regardless of the headline, right? But we are interested in, okay, which one is going to get me the most clicks, right? Or is there even a significant difference between these, right? And so now I see that I have 14 clicks, 8 clicks, and 12 clicks. So I have more than 5, so that's good. So now I can do this permutation test. So what we're going to do is, let's see here. Right, if I use this example, and maybe I wonder if they introduced it kind of succinctly. I'll introduce this as well. Okay. So you're testing 3 different headlines, A, B, and C, and you can run them. Yeah, and then you run them on 1,000 visitors. So of course, these are going to add to 1,000. Make it bigger. Yeah. And overall, right, we have 14 plus 8 plus 12 clicks. So we have a total of 34 clicks, and 3,000 minus 34. I don't know.
2966.
I had to think about it. Like 2,9. Like, okay. Yeah, it checks out. Thank you. All right. And so just overall, right, I had 34 clicks and 2966 non-clicks. Okay. So now looking at 4, 8, and 12, right, it looks like headline A performed the best, right, but maybe very similar to headline C, but headline B doesn't look that good, right? So now we want to know if there's a significant difference between these. Okay. So what can we do? All right, let me go back here. The expected distribution of the clicks, right, would be, okay, then these 34 clicks, these 34 out of 3,000 clicks, they're just going to be spread out evenly, right? So 34 out of 3,000, right? And so what we would have is our expected counts would look like this, right? 11.33, right? 34 split evenly. See here. Hopefully, it looks to me like 34 divided by 3. Okay, so where these guys came from, these are the expected values, right? And so we expect 34 divided by 3, which is 11.33, repeating, right, for each headline. So really what we're looking at is 14 far enough away from 11.33, 8 far enough away from 11.33, 12, right? That kind of thing. Same thing with the no clicks, but we're focusing on the clicks just because that's what we're mostly interested in, right? Of course, we're going to do the calculation for the no clicks as well. Right? Well, we're not going to do anything, but we would. Okay. So then we could go ahead and we could find these Pearson residuals, which is that R, right? Which means that, okay, this is the R. So then I need to square each of those. And then I need to add them all up across the rows and the columns. And we would end up at 1.66 in this case, right? Which we would then take and compare it to the chi-squared distribution, right, with R minus 1 times C minus 1 degrees of freedom. But instead of doing that, right, let's have a look at this resampling algorithm instead. So we're gonna have two ways of generating p-values, right? Either by permutation tests, so like what we're about to talk about, or through that traditional approach of, okay, then it follows a chi-squared, or it's approximated by a chi-squared, and then I can find a p-value that way. So what we're going to do, right, same idea as we have been doing. I've got these 3,000 clicks, no clicks, whatever, and I know that 34 of them were clicks, so I'm going to call those ones, everyone else is zeros, right? So I generate this box of 34 ones and 2,966 zeros. Good. Then I shuffle these and I randomly select a sample of 1,000, right? And I group them into 3 groups. So I'm basically regenerating my data, but randomly, right? But with the same kind of constitution. Then I do go ahead and I find the chi-squared test statistic, right? So I find the squared differences between the shuffled counts and the expected counts, and then I sum them, right? So I do that calculation, okay? And then I repeat this maybe 1,000 times, right? So then I'm just taking the information that I had, okay, I had 34 successes and 2,966 failures, and then I'm just gonna randomly assort them into 3 different samples. And then once I've done that 1,000 times, I can look at how many times out of 1,000 did I have a resampled sum of squared deviations that exceeded what we observed, right? So what we saw in our original sample, right, that's kind of our guide. And then we want to look at, okay, in my kind of simulated results, right, how many of those were more extreme, right? And that's going to be our p-value. So we can do this in R. And I'm just going to do this here. So the chi-squared.test, you can use it. And if you tell it to simulate.p.value equals true, then it does this resampling. So it really just needs the data. And I don't remember what the clicks looks like, but I think it's just a list of zeros and ones. Pretty sure. I'll have to confirm. But I'm pretty sure it's just a list of zeros and ones, and then I can kind of take it from there. Oh, and the group, I guess, ABC. So here, this part here makes it do these steps, right? And I think by default, instead of 1,000 times, I think it does it 2,000 times. Pretty sure that's what that means, right? And then it gives us this p-value, right? So this part does these steps. And of course, you could tell it how many times you want to do it, right? 2,000, 1,000, whatever, right? With an added argument there, right? But what we're finding is that the p-value here is the probability of seeing something more extreme, right? Just from a random sample. So it's quite large, right? So then we say, okay, the differences that we saw are probably due to random chance alone, right? So the test shows that this result could easily have been obtained by randomness, right? And I want to clarify here, since the probability of seeing something more extreme, right, with randomly generated samples, right, is 0.4853. So it's quite large, right? So since the probability of observing differences more extreme by randomly generating samples is 0.4853, which is quite large. In fact, it's a lot larger than 0.05, right, which is our cutoff. So which is large, or I'll say much larger than alpha equal to 0.05. Right, we still use that cutoff. You can change the cutoff if you want to, but that's the default, right? So that's why they're saying that this test shows that these could have easily been obtained just by random chance alone, right? Which means what? It means that the headlines are independent, right? The success of the headlines or the number of clicks that you get is independent of the headlines. So really what we're saying here is, therefore, the number of clicks is independent of the headline, right? Headline A, B, or C. That's good to know, right? Especially if you're kind of running this and headline A is a prototype. I don't know, maybe you're going to spend a ton of money on headline C, but now you've figured out that actually doesn't matter. So then you can save money that way, right? I don't know what the scenario would be, but so now, right, you can say that these headlines, right, they're independent of the clicks and vice versa. And so, right now we've done this test of independence. Okay. It still calculates the chi-squared test statistic, right? But it's with these, no, it's the same, sorry. But the degrees of freedom are not applicable, right? Because we didn't use the chi-squared test statistic. Now, if we kind of scoot along here, first of all, kind of a 1 point less for Python. Because in order to do this in Python, you'd have to use all this. So it's not built in. But remember, R is a statistical programming language, right? So all the things for statistics are built in. But there are things that Python is way, way better at, right? So kind of, it is good to know them both, but in terms of statistics, kind of established things like this, right? R is going to be a lot. It's just one little line. Eee, so cute. Oh, the Python code keeps going. Anyways, whereas if we wanted to use the traditional approach, right, where we use a chi-squared distribution and we say, okay, I can approximate this this distribution with a chi-squared, then I need the degrees of freedom, right? And I need to know what the chi-squared distribution looks like, right? Then I can still use that R function, right? We can run this test. Using the traditional method, right, which is what we would have done, or what we did. The traditional method of approximating the probability using the chi-squared distribution. Using the chi-squared distribution to find the p-value. Right. The code doesn't actually change that much. Right. You're just going to set the simulate.p-value to false, right? So now it's no longer going to simulate. So then it knows, okay, I don't get to simulate anymore. That's fine, right? It takes the same data, right? It takes the clicks, however it's set up. It calculates the chi-squared, but now it also needs the degrees of freedom. And the degrees of freedom, remember, is R minus 1 times C minus 1, which in this case was 2 minus 1 times 3 minus 1. 1 by 2 is 2. Right. And then we get this p-value here. Right. So this is using this approximate chi-squared distribution, but this is how we would typically do it, right? We would kind of find the test statistic, map it onto the chi-squared curve, which is a skewed distribution, but it changes a lot depending on how many degrees of freedom you have. So here's an example. Of a couple of different chi-squared curves, right? So depending on, and maybe on what your degrees of freedom are, if you have 2 degrees of freedom, right, then you're on this kind of tight dotted line. So then it looks like this, right? That's crazy. And then if you have 1 degree of freedom, it's a solid line. If you have 5 degrees of freedom, it starts kind of looking a little bit more skewed, right? And then once you have 20 degrees of freedom, it starts to kind of normalize, right? But if you think about 20 degrees of freedom in terms of R minus 1 and C minus 1, it's going to be really hard to get 20 degrees of freedom, right? So most chi-squared distributions are going to look kind of like this, right? 5 degrees of freedom, that kind of thing. So it's definitely skewed to the right, right? And I would say these all start at 0. And so there's kind of a sharp incline. There's nothing, and then it starts here at the top and then goes. Okay. But these are all skewed to the right. Okay. So then what did this one do? So if we have 2 degrees of freedom, maybe what I'll do is I'm going to map it out over this curve. So the 2 degrees of freedom is here. Right. So that's this one here. And then it calculated the chi-squared test statistic of 1.666, let's say, right? And so what did it do? It took the chi-squared test statistic of 1.66, so this is 5, maybe here. And then it found the probability of being more extreme than that, right? And so then it was able to find this area. And that's the p-value, right? Notice that it only goes to 0.3 here. That's kind of the max, and then flattens out. Okay. I guess it won't make sense without the axes. That's okay. Right, so this is the p-value, which was roughly 0.4348. That's super similar. Whee, my voice. 0.4853, 0.4348, right? Very similar results, right? It just depends on how you get there. Okay. Trying to see. Oh, yeah. So Fisher's exact test, right? It sounds fancy, right? But because it considers all the different combinations, right? All possible outcomes. And then you have this exact probability of seeing what you saw, right? Because you're generating all the possible outcomes. But then in R, of course, it's pretty easy, right? You use Fisher.test and then on the data set clicks, right? And you want to make sure that your data that you enter follows the same format as clicks does, right? I forgot to check what it looks like. I'm guessing it's a column of 0s and 1s and a column of ABC. I'm guessing something like that. But then if you do Fisher's exact test on this data, even though there are more than 5 counts, right, you can still use Fisher's exact test. It's computationally expensive, right, because it considers all possible outcomes. So it might take a while, right? But then you can get this p-value of 0.4824. Right? We can also run Fisher's exact test, which considers, right, just as a reminder, which considers all possible permutations. Good. So for us, right, kind of gravitating towards that resampling technique or the permutation tests, those we use those interchangeably, right? And then, but also it's really good to know the kind of traditional way, especially if you're reading papers or if you're reading kind of publications and that kind of stuff, then of course they're going to be using most likely the kind of traditional statistics. So you don't want to forget about it just because we have this I would argue, easier way of doing things. Right? But you get the same results, so no harm, no foul. And maybe that's what data science is. They're like, well, we got the same results, so, or similar results. Yeah. So, excuse me. So that's the chi-squared, just for categorical data, right? 1 or 2 categorical variables. The multi-arm bandit is kind of a fun idea, right? The multi-arm bandit is another way that you could test, so especially for web testing, right? Where you can decide where, so if people click and say, I want to go to this, your web page, then you can decide which one you're going to show them, right? And then that's a way that you could test your different websites, right? And then you can see, okay, who's going to click on my ad, who's going to click on this, who's going to, you know, who's going to do stuff. Yeah. So the multi-arm bandit, I think it's such a cute name, multi-arm bandit algorithm. So the multi-arm bandit comes from casinos, right? You've got these kind of slot machines. And so you pull on the arm and then and then you win or you probably lose, right? And so the idea is that, okay, you pull on this arm and then that determines which website you're sent to, for example, or what treatment you receive. And then there's some payoff with each one, right? So you either win or you lose, right? And so what we can do is we can use the multi-arm bandit to figure out which one is the best treatment or which one is the best kind of website, right? Or that kind of thing. And so we can use it, because I don't want to write multi-arm bandit again, to assess multiple treatments to help us pick the best one. Multiple treatments to help us pick, and I'll put in brackets the best one, because what we're going to be doing is we're kind of going to move away from the one that's significantly different or significantly the best, because sometimes we don't need that significance, right? Significance meaning a p-value less than 0.05, right? Maybe we're not so concerned about that one. We just want to know, okay, well, out of these 3 options, which one is the best, right? Which one should I be going with? So in the beginning, if you're using a multi-arm bandit algorithm, you're randomly assigning people to random treatments, right? So you've got your set of treatments. Let's say there's 3 treatments, right? So web design, for example, and you're randomly sending people to different designs, right? Then as you see that one is succeeding, right, then you're going to increase the probability a little bit of sending people to that website, right? Or that version of the website, let's say. Okay. You don't want to just go for that one because that was just in the beginning. So then you let the other ones play out. And if one starts improving, right, then you can shift and you can say, oh, send more people to this one. And then finally, you'll start to see which one wins out in the end, right? So it's kind of this interesting concept of kind of an iterative process, I guess. It kind of goes through and says, okay, which one's the best one now? Okay, send more people here, but it starts off where they're all even. And then it starts to kind of figure out, okay, you're the best, so go over here, go over here. Okay, this one's kind of doing a little bit better now than this one. So then you start sending people here, and then eventually one's going to win. So kind of a fun idea, I think. So each treatment, let's just outline. So for example, website design or ad design. Right, maybe it's as simple as you've got an ad on a website and you have 3 different versions of it. Which one is going to get the most clicks, right? So ad design, for example, is shown randomly and equally. Then we keep track of the wins, we call it, just because of the multi-arm bandit comes from the kind of the casino or slot machines, right? And so call it a win, right? And so a click is a win. Yes. So we observe, which means we record, of course. We don't just watch it happen, we keep track of it. So we observe the wins. Right, so for example, someone clicking on an ad. For each treatment. If one treatment starts to outperform the others, right, it'll be shown more often. If one treatment starts to outperform the other treatments, by some metric, right? So how do we measure if it's outperforming? Well, probably the clicks, right? So for example, more clicks. It will be shown more often. We continue to show the other treatments, right, so that we can make adjustments over time. Oops, we continue to show the other treatments. So we can make adjustments over time. So that's kind of a fun idea. I don't know if they have any, I haven't looked yet. Did they do any R code or did they just explain it? They did not. There might be some though. I'll have a look. Not, it's just a theoretical idea. I'll have to look up how to do it in R. Okay. So the multi-arm bandit is just a way of comparing multiple treatments, right? Figuring out which one is the best one, which is really going to be our goal, right? In data science, it's not so much which one is significantly better than the others, right? We're just trying to get things out there. One thing that we want to talk about just to wrap up the chapter is effect sizes and also I guess how they relate to sample sizes. So an effect size is basically how large of a difference do you need, right? And so, for example, if we're thinking about this multi-arm bandit, right? How large of a difference do you need before you start shifting the views, right, to a specific headline or ad, right? So you need some sort of gauge that says, okay, once I'm seeing, more than 20 clicks, right, on average, more in, I don't know, ad A than ad B and ad C, right? Then I'm going to start shifting. So I need to have this kind of effect size, this idea of this effect size here. So the effect size is the minimum size of the effect, right, that you hope to be able to detect, right? So if the difference is not large, right, then that's, I don't know, it's not that important, right? So it's going to be the minimum size of the effect you hope to be able to detect. For an example, right? What if we want page A and page B to differ by at least 20 clicks per day? Right, then that 20 clicks would be the effect size, right? But it depends on, so then the size of the effect size, I guess, depends on the actual number of clicks, right? And so is it 60 versus 80, or is 20 kind of lost in the shuffle, right? And so we want page A and page B to differ by at least 20 clicks per day. To say that they are significantly different. So here, this 20 clicks per day, right? Let's assume that this is a large difference. Right, so for example, page A has 60 clicks and page B has 80 clicks. Right now, the difference between these is 20, right? But this is going to feed into the sample size, right? If I'm comparing 60 and 80, then 20, I'll be able to pick up on that, right? But if the effect size, right, is small, then we're going to need to increase our sample sizes, right? If I want to be able to detect and say that there's a significant difference between a close number of clicks, right, then I need to increase my sample size. Yeah. So for our sample size, I'll say for large effect sizes, right, which really means to detect large differences. Right. So if there's a huge effect size or a large effect size, then we don't really need to collect that much data before it starts showing that, okay, there is a difference here, right? But if we're looking for an effect size that's quite small, right, then we would need to collect more data, right? We'd need to increase our sample size. So for large effect sizes, we do not need large samples. Oops. As large differences would start to emerge almost immediately. Start to emerge almost immediately. Right. And then on the flip side, for small effect sizes, right, we need larger sample sizes. Small effect sizes, we require larger sample sizes. Oops, larger. Right, if you're trying to detect a small difference, right, then you need to kind of be really sure about that. Okay. Good. That's it for chapter 3. I'll leave it there. So test 1 up to this point, right? Let's write that down here. Up to this point. I'll see what I can come up with for some sort of review. So I do have a review block scheduled. So I'll see what I can do. And yeah, then we've got the test 1 on Tuesday. Any questions?
Do we need R for test 1?
No. I might give you our output to look at.
Do we need any calculator?
No. I had to think about that one. No, no calculator. I'll bring some just in case. Sometimes it feels safer to have a calculator, but you won't need it. Okay. That's great. Then I'll stop this recording. I almost forgot.